Hello. This section covers the core concepts of a rigid body for simulation purposes. While rigid body physics is a complex field with extensive literature, here we provide a brief overview to set a foundation for implementing numerical integration, as utilized in the Newton Dynamics Physics Library. For a deeper exploration, resources like Wikipedia are of great help. The technical introduction to rigid body simulation is provided in the download document Rigid Body Dynamic Intro. We present series of examples for understanding rigid body dynamics blueprints, starting from simple models and progressing to more complex and unintuitive cases. Example 1. A solid sphere. A solid sphere serves as an approximation to an ideal point mass. This object has three axes of symmetry and equal principal moments of inertia along all three axes. Due to this symmetry, a solid sphere conserves not only its angular momentum, but also its angular velocity. This property makes it an ideal introductory example for understanding rigid body dynamics. Example 2. Solid versus hollow cylinder of equal mass. A cylinder also has three axes of symmetry, but it can have different moments of inertia along its length axis as compared to its other two principal axes. For example, in a hollow cylinder, the moment of inertia along the length is greater than that of a solid cylinder of same mass. This increased moment of inertia makes the hollow cylinder more resistant to rolling. Example 3. An egg-shaped elliptical object. This object, known as a phytop, resembles an egg-shaped sphere. When a phytop spins on a surface with some friction, it behaves uniquely. At a certain angle, the ground friction creates a torque that is misaligned with the object's spin angular momentum. This misalignment causes the total angular momentum to align along the longitudinal axis, which makes the object's center of mass rise. Example 4. A rigid body with three different principal moments of inertia. In this example, we examine a rigid object with three different principal moments of inertia, such as a book, a cell phone, or a tennis racket. When these objects spin in a zero-gravity environment, without external forces, they exhibit surprising behavior. When we expand the Newton-Euler equations of motion, we find that two of the three components of the gyroscopic torque are negative, which indicates that these components contribute to stability. However, the component along the axis with the middle moment of inertia is positive, leading to an unstable fixed point. As a result, when the object rotates around this axis, it cannot maintain stable rotation and periodically flips. This phenomenon is also known as the tennis racket theorem or the Zannebekov effect. We now are prepared to create our first blueprint control physics objects. In this demo, we'll utilize the gyroscopic behavior of a wheel with three axes of symmetry, where two of the principal moments of inertia are equal. The theory for how this body works is in the download doc physics of Will Bike. We start by making a model from a paw actor, so the model can receive player inputs. On the input event, we store the longitudinal and lateral axis values in two local variables declared in the blueprint. The Bond-Newton force and torque custom event calculates the external force and torque applied to the body at each time step. This event functions like Unreal's tick component, but is synchronized with physics simulation time. We now write the blueprint code for applying external force. Gravity acts by default, but we'll add a zero force vector for clarity and future reference. Next, we write the blueprint code to calculate the external torque. The external torque has two components. The engine torque, which is applied along the axis of rotation of the wheel and provide the wheel main angular velocity. The turning torque, which is a fixed torque along the axis of traveling of the wheel, designed to lean the wheel to the side, causing a constant precession velocity. Adding these two independently calculated torque components and apply the result to the rigid body. We can now test the blueprint in our scene. We check that each control make the vehicle act as expected. Turning while the engine velocity is too small will cause the wheel to flops. Moving forward and backward should accelerate the wheel until it reach a terminal velocity. We can test drive the model. With a little practice, the wheel should drive straight and turn left and right. With more practice, we can even drift, something professional motorbike drivers can accomplish by losing traction of the rear wheel while countersteering and leaning at the same time. All clips are taken under the fair use policy, and the original links are provided on the description below. In the next video, we will introduce constraint joint. Thanks for watching.